MLOps for deep learning. So just a brief intro to who I am. I'm the CEO and co-founder here at Spell. Prior to working at Spell, I spent about a decade at Facebook, where I built the newsfeed systems, ran the newsfeed team, and designed the feed ranking algorithms. I moved to New York and I started the Facebook office here. And most relevant to Spell, though, in 2014, I co-founded Facebook AI Research, which is now one of the sort of top AI research groups in the world, with Jan LeCun, one of the sort of early researchers in AI, and just won the Turing Award, actually. So my job at Facebook AI Research was to build up our engineering team and to build the tools and the infrastructure that we needed to power the AI research that we were doing. And that was a lot of the inspiration for Spell. I want to point out that we spent, our budget for Facebook AI Research, more than 50% of our budget was dedicated to hardware and software infrastructure. And I think that's something that we've seen. There was a McKinsey report recently. The sort of best teams in enterprise, the teams that are really considered AI leaders in their industries, they tend to spend more than half of their budget on tools and infrastructure, because it's so important. Our mission is to make AI easier and more accessible. And so MLOps for deep learning, what we're really trying to do is build the tools that make it much easier to use, to train and deploy models, and hopefully with that, facilitate AI becoming and machine learning becoming a part of all the products that people use on a day-to-day basis. There are two sort of main challenges with deep learning particularly, and using it in an operational sort of real world environment. The first is that the infrastructure is really intense. On the right here, you can see this chart. This charts the sort of state-of-the-art techniques across a different number of applications. And you can see it's on a log scale, where it's measuring the rough amount of compute in petaflops that it would be required to reproduce this work. And you can see there's this first era where, even on a log scale, there's this ever-increasing exponential growth in the compute requirements for AI applications. And then you can see, starting in 2012, when GPUs and deep neural networks came onto the market, you can see an even faster acceleration in just the raw compute required to do some of these things. I guess one data point that I like to point out is something like AlphaGo 0 or GPT-3. These are on the order of billions of parameters. Our estimate for the brain is that it's somewhere around 40 trillion connections, synapses between neurons. So there's definitely, with neural networks, the more intelligent the application, it seems to be the case that bigger is better, and scale matters. It's not just the scale of the model, by the way. It's also the scale of the tools, the flexibility, and it's also the ability of the practitioners to make use of large scales of compute and experimentation. So challenge one is that the infrastructure is really intensive and requires a lot of infrastructure to be built to get started. The second challenge is that machine learning is different than traditional software. So traditional software, typically you build it, you test it, and then you deploy it. But machine learning works with a really different workflow. And it involves a lot more of these feedback loops. So places where you learn something at a later step that means that you have to go back and update something that you did along the way. So it doesn't have this sort of very direct feed forward thing. And that means that where in DevOps, it's very easy to piece together different pieces of the workflow with different tools, and you have a sort of like DevOps stack that emerges with different tools being used at different places. With machine learning, that's a lot more difficult to do, because if those pieces aren't really intelligently integrated, going back in time and recreating something ends up being really cumbersome. And that's a big part of the workflow of machine learning. So you want to make sure that that's something that you facilitate and make easy. So that's why we built Spell to be end-to-end. We take models all the way from experiment orchestration from the first experiment that you've ran, all the way through comparing multiple experiments, hyperparameter optimization, building a database of models, deploying them, and ultimately monitoring them, all on top of the same infrastructure. So we're end-to-end, and we can run on top of any of the major clouds. We can run on top of on-prem hardware for compute, Kubernetes or Slurm clusters, and we can mix and match these things. So we really are fully infrastructure agnostic and fully hybrid cloud. I want to talk about two sort of base concepts that really Spell is built around. The first is remote execution. So when you go to run a machine learning experiment, there are a lot of things that you have to define. You have to put code in a certain place. You have to identify which data you want to use. You have to assemble it all so that it runs seamlessly. And what we found is that the easiest interface to introduce people to experimenting with machine learning is just to borrow something they do every day, which is just running something on the command line. So we built this command line tool, Spell Run. This is one of the first things that we launched that will automatically take whatever command. If you put it before a command, we'll automatically assemble everything that we need to move execution of that command onto the hardware in the cloud or on-prem that you've set up as your Spell cluster. So we really like that this is the simplest way to introduce people to the platform. It's something that everyone does, and it's something that's very intuitive. And on top of that, though, even though we're providing this very sort of seamless, easy way of executing things, behind the scenes, we're tracking a lot of the details and making sure that everything we run on Spell is well structured and reproducible. So when you run something on Spell, we keep track of the exact code state via the git commit hash. We build and keep track of the environment, so we know exactly which Docker file we use. We take hashes of the environment that was run in. We know exactly what data was attached and put in one place in the container, and what hardware it was run on. So all these things combined are a precise definition of an experiment. We like to think about moving from, I ran this code, to I want to know the answer to the question of what will this code in this environment, on this data, on this hardware, what is the answer to what will happen if I run that experiment? And so Spell is really about, very seamlessly being able to move workloads and sort of throw things up to a cluster and have them run on much more powerful hardware. But also underneath that, having this net of precision and reproducibility that over time gives you a more efficient, reliable, and sort of a better workflow around deep learning. Just a couple features I want to call out before I get into the demo. Things we support, we have a whole Cloud Jupyter system. We integrate with Git. We support using spot instances and also cloud credits. So if you're looking to make the most use of credits and you want to use spot instances, we can layer on top of your cloud account, and your credits will get applied to runs that you do on Spell. We support distributed training. We have a whole custom hyperparameter optimizer that's built on top of Spell runs. It's very easy to use. We have an integration with weights and biases, so if that's a tool that you're used to, Spell runs can automatically populate data into that interface. Once you have models, we have a model versioning system where you can collect multiple versions of the same model. We automatically deploy to Kubernetes clusters within your cloud once you have those. You can use custom server handlers, so you're able to write in code anything that you want your API to do, very flexible there. We support batching on GPU, so if you are running a model that requires a GPU in production, batching drastically improves the performance and is kind of necessary to using those things for inference. We have a whole workflow automation system, so anything you can do on the platform, you can also script out and automate. We integrate with CI and CD really well, including GitHub Actions, and we provide a automatically deploy a Grafana dashboard, so you get really detailed views into the clusters that you're using and how that hardware is performing. So I think now I'm going to jump into a live demo. Let's go back to sort of beginning here. The demo here is going to start with the command line. So As I mentioned, we have a command line tool that makes it really easy to send anything up to the cloud as a reproducible experiment. Here, I'm in this code right now. This is genuinely just the PyTorch examples repository. This isn't any custom baked demo that we've done. This is just code that we found in the wild. In this case, the examples that come with the PyTorch library. And here I'm going to run this word language model, an NLP application. Uses neural networks, going to be much more efficient on a GPU. So if I wanted to run this locally, I would type this command. I would use Python to run that Python script. But to run it on spell, all I do is type spell run in front of that exact same command. And this is going to automatically move execution of this up to the spell cluster. And I get a lot of different command line options that can control how this is run. In this case, I'm going to use the machine type flag, and I'm going to request a type machine of type T4. This is going to have a GPU attached, and it's going to run a lot faster than just on CPU. So if I run that, what spell is going to do is synchronize the exact state of the code via Git. It's then going to build a container that contains the code, any dependencies that I needed, and it's going to put that container, find a machine of the type that I requested, put that container onto it, set up logging of the command logs, any metrics that come out of it, and any outputs that are written to the file system. It's going to start the process and start streaming me back the logs. So from my perspective, this feels kind of like I just ran this command, but execution is actually happening somewhere else. It's happening on, in this case, on AWS. So this is running remotely. I can Control C and stop tailing the logs, but the run is still running, and I can go over and see that in the web interface. So here's that run in the spell interface. As you can see, we have all the details. We have the repository and a link to it on GitHub. We have the commit hash for that code. We have the exact command that was run. We have the machine type, and we know that it was run on our default container. If I want to, I can click this button, and because we know all those details, I can run an exact copy of that experiment at any time, or I can change any of the basic parameters. I can add environment variables, etc. It's very easy to reproduce runs once they're on spell. But back here with this experiment that's running, we're automatically collecting metrics from the machine learning framework itself. So here I can see different epochs as it goes through the data multiple times, seeing the individual batches that get sent to the GPU with each epoch, how many milliseconds each batch is taking, loss, perplexity, sort of all the basic things that I would want to monitor about the training process. I also get hardware metrics. So here I can monitor CPU, memory, network, and GPU utilization, GPU memory, disk usage. And one feature I didn't call out in the first version of this, but I think is useful too, is that just another like little feature, part of what we do at Spell is like build little things we know you're going to need that will probably help you. If you write too much to disk, you will run out and your experiment will fail. And so we have a daemon that runs, I think this is AWS only, that will automatically detect if you're getting close to filling up the disk. It will go into the AWS API and automatically expand the EBS volume when you get close to a threshold. So just I think worth calling out, like little things like that that can really save you from losing work are built into Spell. So I get all these metrics both from the machine learning process and also from the hardware. I can also write custom metrics. There's a Spell metrics log one-liner that I can add. I can log time series of anything that I want to track. I can log images. I can log text. All of those will get stored in the metric system, and you'll see here in real time, and will get stored permanently. Also, all of these metrics are available via the Python API in real time or after the experiment's done. So it's very easy to pull up and do sort of custom analysis on any of the ML that you've done just by going to the API and pulling these metrics by the experiment ID. Down here, I get the sort of live streaming of the logs, and then the final thing that we collect is anything that's written to the file system during the run we track as an output of that run. So in this case, this model is writing a serialized version of the model every epoch. So I can see that here in the web interface, and at the end of the run, that will get written back to what we call SpellFS, which is the shared file system that layers on top of all of your different storage systems, organized by experiment ID. So we will write back any outputs from any experiment into this runs folder by the experiment ID that created them. There are two things that's nice about this. One is that it's much more organized to have the artifacts of every one of your runs, the final models, linked directly back to the experiment that created them, and then also to the code that was run, et cetera. This is just one of the sort of automatic model lineage features that we built into Spell, so you never lose track of the ultimate sort of beginning of where a model started. It's also nice because having everything in the cloud means you can automatically mount this into another experiment. Everything, you never have to worry about copying data. We always mount it remotely and then cache it on the local machine in real time. So all of the sort of storage systems that you link into Spell just work and can be mounted instantaneously into experiments. Alongside running these experiments from the command line, we also have a Cloud Jupyter feature that we call workspaces. So not only is this a way of running Jupyter notebooks in the cloud, but it also comes pre-baked with the details of the environment that you need to run them. So you can add things to the container environment that Jupyter is running in here, and they will persist. But also allows you to attach different data from the shared file system into the container, and that will persist. So what you get is a Jupyter notebook that not only can run in the cloud and you can run from anywhere, but it will also automatically come baked with the libraries that you need in the container and the data attached in the exact place that you need it to run your analysis. So that's Cloud Jupyter. We also have a hyperparameter optimizer. So because we're orchestrating all the experiments as well as keeping track of their metrics, hyperparameter optimization is super easy on Spell. All you really have to do is, instead of using the run command, you use our hyper command. And when you use the hyper command, you can put tokens anywhere on the command line or in your code about different hyperparameters that you'd like to experiment with and test. When you've done that, you run. We will prompt you for ranges that you'd like to search over. We'll ask you for the strategy for the hyperparameter run or the optimizer that you want to use. We support grid search, which will just iterate over values, random search over the space, or updating or Bayesian search here. We'll ask you how many experiments you want to run. In the case of Bayesian, since it's iterative, we'll ask you how many you want to run in parallel before we start suggesting new values. And then we'll ask you for a metric that you'd like to optimize for. So here, this is training this CFAR 10 model, so a basic computer vision model, optimizing over a couple different parameters in the model, optimizing for validation accuracy, and we're going to run 30 experiments using a Bayesian optimizer to suggest new runs. So here I can see a summary of the performance of all the models, both as a chart, so I can switch from accuracy to validation loss, right? I think this must be a huge amount of data, so it's having trouble rendering. But I can see the results across different metrics in this chart. I also get this summary table, which will summarize the experiments in a table. And for each of these experiments, they are still a fully reproducible Spell run. So I can click into each individual experiment, and I can see how that experiment performed with metrics, hardware metrics, and I can click into the models that were serialized from it and even view logs. And then down here at the bottom, I get these facet charts, which are just projections of the experimental results across each of the different hyperparameters that I optimized for. So I can see how this hyperparameter performed relative to the experiment results. Same for kernel sizes and for the dropout values. Good example is if you drop out all of the parameters, it turns out eventually the model doesn't perform very well. So, some sort of obvious things that you can see there. So that's our hyperparameter optimizer. I think one thing that we found is, running a hyperparameter sweep is one of the easiest ways to improve the performance of a model. It's basically free money where you know enough that you can ask the machine to do the remainder of the work for you, and that can happen totally asynchronously. However, it's hard to orchestrate. It's somewhat painful to get multiple experiments to run, to vary one thing about them, to make sure you're keeping track of them, to compare results, et cetera. And so because Spell automates all of the infrastructure, it makes running a hyperparameter search really easy. It's something that people can do more often, and it's one of our most popular features. So that's hyperparameter search. The final sort of advanced experimentation feature is workflows. So we built a really scriptable system on top of all the APIs that sit behind Spell, where you can write with just basic Python, without having to use some sort of like DAGified system like Airflow. You can write a basic script and run through a more complicated workflow of different operations on Spell, all from Python. So that might include things like spinning up 10 runs in parallel, checking their metrics to see which one is performing the best, and then killing the ones that aren't. Or it might be, taking the outputs of one run and then using those as inputs to another run to do some model evaluation, some data pre-processing, that type of thing. Or it could be a full end-to-end, collect an updated data set, do some preparation on it, run it through a training system, send an email to yourself saying we have a new candidate model, add it to the model versioning system, deploy it as an endpoint, and then run a couple of examples through it, as an automated workflow. So really kind of anything that you can do on Spell with our training, our optimization, our deployment, and our monitoring system, you can script as an end-to-end workflow just using Python that we will run asynchronously. And so for all workflows, we keep track of the individual runs that were run, and you can click into these and see exactly what happened in the logs. So very powerful system for weaving things together. I want to pause right there. That was a ton of stuff. Sydney, would it be? Are there any questions in the chat, or anything that we should? Anything that we can answer?
No questions so far this time around.
Awesome. Great. Let me jump into deployment. And actually, for variety, I'm going to start with the demo that we have.
And while you're bringing up this demo, if people in the chat could share, we're curious to know, what does your MLOps process look like now? Are you using infrastructure that you've built in-house? Are you using open source, using tools like Spell? We'd love to have an idea of kind of what your flow looks like right now.
Yeah, that's a great question. I would love to hear what people are using now, and what kind of the most painful point of their workflow is at the moment. So this is a fun demo we built to sort of showcase Spell and our deployment capabilities. We trained a generative network to identify sort of different objects in paintings. In this case, we trained it on Bob Ross paintings. And once it's identified those things, you can create on the left here a little segmentation map of where you'd like different objects to go. In this case, I'm going to draw some happy trees. And let's see if we can make these a little more realistic looking. Yeah. And so I'll draw some trees. I'm also going to put a mountain in the distance. Let's say like just a little one kind of coming in here. And then I would like a, you know what, I think we'll do this by the ocean. So let's make it, let's see if we can put some ocean over here on the left side of the screen. And so when I click run here, this is going to take this image, send it to one of our model servers that's serving this generative model that will look at where I've identified things and try to fill in those pixels as best it can, and try to recreate the look and feel of a real Bob Ross painting. So let's see what this comes up with. All right, not too bad. So we can see we have the ocean here. The trees came out pretty good, I think, and then a mountain in the distance. So kind of a fun demo, but really, all of this is running on top of our model serving infrastructure. So going back to the UI, I'll kind of work through how I can deploy a model once it's trained, and then we'll see this model specifically. As we can see here, this is my experiment. I'm training this language model. It's still running. It's on Epoch 16, and as before, it's constantly serializing a copy of the model to the file system. So we're tracking that. If this is, I might take this and move it into a hyperparameter search and try to get the absolute best performance before I do this. But let's say I just wanted to deploy this. I would click this Create Model button. And I can take that model and any other files, so I can attach other assets. There might be other things that I want to package together, but that collection of files will get added to the registry as a model. I can give it a name. I can version it. This can either be auto-incrementing numbers, which is the default, or you can add tags like, production, test, that type of thing. And then you can add some notes as metadata for it. And that will go directly into our model versioning system. So in this case, that Paint with ML model, that's version 1, and that's sitting here. Now, because, again, the model lineage is really important, knowing exactly how something was created. So here, even though this model, this is version 1 of this model, because it was created from the outputs of run 10.11, we have that context. We can click back into the exact run if we want to, and we could recreate that model from scratch. So once I have a model in the registry, I can go into our serving infrastructure, and I take that model and I pair it with a handler that will have access to it. So here you just implement a basic handler function that will get fed inputs from the API. You run them through your model and can decide on the outputs. And then I also pair it with a container. In this case, I've used just the spell default container, probably the same one that this was trained on, but I've added some pip requirements to it. So we'll build something that includes these pip packages. You can also add apt packages if you need stuff built into the OS, or we also support conda files. You also can provide your own container, and that can be a GitHub tag. It can be in a private container registry that you've registered. Any of those different things. And once I pair those things together, we will deploy them as a URL, an API endpoint here automatically, and we'll turn on auto scaling. In this case, you have a bunch of different options for how you can set up the auto scaling. You can have it auto scale by CPU utilization, by request rate, GPU utilization, request per second, that type of thing. As I mentioned, we also support auto batching on GPUs, so this is a huge performance win when running models through big beefy compute like GPUs. Here, it looks like some people have been trying the model. That's great. Here you get, you can see basic metrics like total requests, any failures that happened, requests per minute, median latency, 90th percentile, etc. This is the same metric system that we use in experimentation, so it's very flexible. Not only do you get these default metrics that are coming out of the API itself, but you can log any custom metrics that you want. They can be images, they can be text. The metric system is designed to capture all of the things that you might want to know about a model, either while it's being trained or in production. You also get hardware metrics per pod, so you can see the CPU utilization and how many cores are active, memory usage, etc. And you get logs for individual pods if you need to debug things. This is one way. For a sort of another way of looking at the hardware underneath this is our Grafana dashboard. We automatically deploy this as part of the serving cluster when you sign up for Spell. So this is something you can click into and get even more detailed look into how your hardware is being used and how the cluster is performing. The sort of final thing that I want to show is I'll run this one more time and just showing how that request shows up in the metric system alongside the model server. Let's see, what do we want to do here? Let's add some, let's add a rock over here. That looks like a rock. And then maybe some plants. All right, so we're gonna get another version of our slightly more interesting Bob Ross painting. Okay, so we get some plants growing and a little rock in the corner. We can see that request coming into this model server. We can see it in the Grafana dashboard. We'll see a little spike in CPU utilization. Let's see if that shows up. This might be delayed by a couple seconds, so we won't wait for that. But then I can click from that model into the exact version of the model. And I can click from this model registry back to the original experiment that created it. So not only do we have a model running in production, we're monitoring it, it's auto-scaling, we know everything about it, we have a lot of flexibility and production readiness in the infrastructure around it, but we also have a precise record of exactly how it was created, all the way back to the commit hash of the code and the versions of the data that went into generating it. Just to wrap up after the demo, this is something you can try yourself. Deploying a Spell cluster takes about 5 minutes. We support all of the major clouds. All the instructions are super clear. If you want to try a cluster, it's free. Here's the URL that'll walk you through it. Very easy to get started, and you can do all the things that I was just showing immediately. And also, we're hiring. So if you're interested in charting a course for the tools that make AI and ML a reality for teams and a real part of the products that we use every day, that's what we're doing, and we'd love to hear from you. So check out our careers page on our website at spell.net.